This is the same drawing that is on page 55 of your textbook, and we're going to use this drawing to determine what the limit as x approaches 0 of sine x over x is. So let's first identify the three areas, or three regions whose area we're going to determine. So first, this pink shaded area is a triangle OMP. So that's this region here, this triangular region. The second region is the sector, so it goes all the way out to the circle, so that's this area, and clearly that sector's area is larger than the pink triangle's area. And then finally we're going to look at the area of the triangle all the way out to this line, and so it would be this entire region, here. And so it should be clear that the pink shaded region is less, or the area of the pink shaded region is less than the area of the pink shaded region plus the green shaded region, which in turn is less than the area of the pink shaded region, the green shaded region, and the blue shaded region. Let's also make note of the fact that this circle that starts here and continues this way is a unit circle. So the length from the origin to here is 1, and the length from the origin to here is 1, as we have noted here and here. Now, next, let's verify that this height right here is actually sine x. So sine x is defined as the ratio of the opposite side of a triangle to the hypotenuse, but the hypotenuse of this triangle is 1 right here, so it is the same as the opposite over 1. So that gives us sine x equals the opposite over 1, or sine x equals the opposite side of this triangle, and therefore this side of the triangle is sine x. And just to be clear, the triangle that we are referring to that had this side as its opposite and this side as its hypotenuse is the triangle OAP. Now let's see why this side of the largest triangle is labeled as tangent x. That largest triangle is the triangle OMQ. And so the tangent of x is defined as the ratio of the opposite side over the adjacent side, but the adjacent side of that triangle is this side, and so the adjacent is 1. The opposite side of the triangle is this side right here that we're trying to find. So we have that the tangent of x, is therefore equal to the opposite side of the triangle, which is this side, and that's why we have this side labeled as tangent x. So next, let's recall that in determining the area of this pink triangle and this largest blue triangle, we're going to use the area formula for a triangle 1/2 base times height. And for determining the area of the sector, which is the pink shaded region plus the green shaded region, we're going to use this formula for the area of a sector. So the area of a sector formula is 1/2 the radius squared times the angle. In our case here, the radius is 1, and we should have had this label for this angle we're labeling as x. And let's just note why this formula for the area of a sector makes sense. If we're going around the whole circle, then that would be 1/2 the radius squared times the angle around the whole circle, which would be 2 pi, and so this gives us the familiar pi r squared formula. And so that's how we justify that this area of the sector formula is correct. It is actually just taking the portion of the area of the circle that we need. So filling in the areas for the triangle, 2 triangles, and the sector underneath them, the pink shaded triangle has a base of 1 because the base is the radius, and it has a height of sine x, so its area is 1/2 the base times the height, 1/2 1 times sine x. The area of the sector is 1/2 the radius squared is 1 squared, and the angle theta we have said is x. So 1/2 1 squared x. And then the area of the largest triangle, it also has a base equal to the radius. Right here is its base, so it is its area is 1/2 the base times the height, and the height is tangent of x. So if we put the relationship between these 3 areas in succinct form, we wind up with this set of inequalities, and we're going to look at that set of inequalities on the next blackboard. So here we have the string of 3 inequalities that came from the picture on the previous slide, and what we want to do is get sine x over x in between the an inequality less than it and an inequality greater than it. So what we're going to do is we're going to divide, or actually we're going to multiply by 2 over sine x. When we multiply by 2 over sine x, that gives us 1 on the leftmost inequality. It gives us x over sine x in the middle inequality, and it gives us tangent x over sine x on the rightmost inequality, and the tangent x over sine x that we get in this rightmost position reduces to 1 over cosine x. But of course what we want is to have in this middle position right here sine x over x. So what we have to do is flip all 3 of the inequalities. So let's take a look at what flipping inequalities does to the direction of the inequalities. So this string of inequalities is a valid string of inequalities. A third is less than or equal to 1 is less than or equal to 3/2. What happens when we flip each of the three elements here, each of the three numbers involved in the inequalities, or take the reciprocal of them? So the 1/3 becomes a 3, the 1 does not change, and the 3/2 becomes a 2/3. But clearly we cannot say less than or equal, less than or equal. And what happens when we flip inequalities? We change the direction of the inequalities. So we're going to use that inequality rule to flip this set of inequalities. So we flipped each inequality and changed the direction, and we see that sine x has above it the number 1, and it has below it cosine x. So now let's take the limit as x goes to 0 of the outside value right here, or the outside function, as x goes to 0, and we look at the cosine graph. Cosine graph looks like this about x equals 0, and so as x goes to 0, the cosine goes to 1. As x goes to 0, the function 1 does not change. It already is 1, and so it just stays at 1, and therefore our sine x over x is both less than or equal to 1 and greater than or equal to 1, and so it must itself be 1. So we arrive at the conclusion to the question, what is the limit as x approaches 0 of sine x over x? And we see that that result is 1. In the next video, we're going to use this limit, that the limit as x goes to 0 of sine x over x is 1, to determine what the derivative of sine x is. I know that we already know that it's cosine x, but we're going to verify that the derivative of sine x is cosine x. So that concludes this video.